Our first topic is actually a bit of a sideline from the main theme of this course. Decision theory is the study of what happens when only one agent is making a decision. So it's a sort of degenerate case of game theory where there is no game, there is only kind of one agent alone. And really, decision theory is the study of what preferences can be for an agent. So specifically, both in game theory and in a lot of other places, for example, in machine learning, we use numerical valued payoffs. And decision theory is partly the study of what's really going on when we use numerical valued payoffs. And nobody hardly ever talks about this. So the purpose of this segment is kind of to clear up some misconceptions about what's really happening when we do numerical valued payoffs. So one of the basic setup is like this. We have an agent who has to make a selection from a set of choices. And agent could be a human, or for our purposes, because we're computer scientists, an agent can also be a computer program. So there's a slightly gnarly question of what does it even mean to be an agent? And for that, I personally like to use the slogan, an agent is anything that has agency, which doesn't answer the question. It just shifts the question into a different form, which is, what is this mysterious property that we call agency? The ability to make decisions freely. Anyway, so we have an agent who has to make a selection from a set of choices. And we're going to assume that this set of choices is known to us and to the agent, and that it's fixed, it can't change. So if you're an economist studying human decision making, then this is a bit of a sketchy assumption. But luckily in computer science, our lives are a bit easier because it's quite often safe to assume that the set of things that your program can do is fixed up front by the designer. Okay, now, as well as the set of choices, we're also going to have a known and fixed set of possible outcomes. So these are things that can happen as a result of your choices or the agent's choices. And we're going to say that the mapping from choices to outcomes is not going to be deterministic. In general, this is a probabilistic mapping. So we get a conditional distribution on outcomes given choices. So this is traditionally written like this. I kind of like to write it like this, as a function that given any choice will give you back a probability distribution on outcomes. So I'm writing delta y for the set of distributions on y. Okay. Now on outcomes, we're going to have preferences, and by we I mean either the agent in question can have preferences, or if the agent is a program, these preferences could belong to the programmer, and this is heavily context dependent. So we want to say that, so if y and y prime are two different outcomes, that is to say two different elements of y, then we can say that y is weakly preferred to y prime. So this is something like the agent thinks that getting the outcome y is at least as good as getting the outcome y prime, so they're at least as happy. And okay, so it can be the case that we have two outcomes and the agent is at least as happy with either as the other, in which case we're going to say that the agent is indifferent, and we're going to use this notation for that. So if it's the case that y is at least as good as y prime, but y prime is not at least as good as y, this means that y is kind of strictly better than y prime. So the agent kind of strongly prefers, in some sense, to have y than to have y prime. And in this case, we're going to use this notation. So this is a curly version of greater than and a curly version of greater than or equal to. I'm using a different notation because this has most but not all of the same properties as the normal greater than sign for numbers. Okay. So what So when we say that this means preferences, we're kind of implicitly assuming a couple of properties of this thing. One is we're going to assume that for any two outcomes, the agent is going to weakly prefer one to the other. And it can be that they're indifferent, in which case they prefer both. So we're not allowing it to be the case that the agent has no preferences. Or rather, if we would think intuitively the agent has no preferences, we're going to encode that as saying both, so they're indifferent. And the other basic property, so that first thing is called totality, the totality of the preference relation. The second property is called transitivity, which is that if y is weakly preferred to y prime and y prime is weakly preferred to y double prime, then y is strictly preferred to y double prime. So you're kind of not allowed to have kind of loops in your preferences. So this thing forms a mathematical structure which is called total preorder or a preference relation. So this is a kind of minimal definition of what preference can even mean in abstract terms. Okay, so here's where numbers come into it. So when you have some outcomes, we can sometimes represent preferences on those outcomes by a thing called a utility function, which is a mapping from outcomes to, here I've written real numbers, which is the mathematical object. In computer science, of course, we're going to normally use double there. So just a thing that represents continuous numbers in a good enough way. So this is a thing that you can sometimes do satisfactorily and sometimes you can't do. So the idea is that we're going to arrange things so that if you have any pair of outcomes with one strictly preferred to the other, that happens precisely when the utility is greater numerically. So this is an inequality of ordinary numbers, and that indifference happens exactly when these numbers are equal. Okay, there are two benefits to doing this. One is using real numbers, of course, makes calculations a lot easier. And of course, you're all studying machine learning, so you know something about the unreasonable power of optimization of real numbers. If you don't do this, then you're doing kind of discrete optimization in general, which is very hard. The other reason, which is a lot more conceptual, is that if we do this, then if you don't have a fixed element, a fixed outcome, but instead you have a probability distribution on outcomes, then we can also get a numerical rating of that because we can use expected utility. So if you get a real number, real utility for every outcome, then you can get an expected utility for every probability distribution on outcomes. Okay, as an aside, I'm going to show you how I like to think about probability distributions on sets of possibilities. So these things are kind of geometric. The key word here is simplex. A simplex is a higher dimensional triangle. So if we have only one possible outcome, then there is only one possible probability distribution on it, namely do that thing with probability 1. So that just looks like a point. If we have two outcomes, then the probability distributions on this can be visualized as a line segment where at one end you have do x1 with probability 1, at the other end you have do x2 with probability 1, and in the middle you have 50-50. So for example, here we do x1 with probability, say 2/3, 1/3, and x2 with probability 2/3. If we have three outcomes, then we can draw these as a triangle. So here we have do x1 with probability 1. Here we have do x1 with probability 1/2 and x2 with probability 1/2. And here in the middle, we have do all three things with equal probability. So all the points inside this triangle represent kind of different weightings of these three things. And then if you have four outcomes, you need to go to a tetrahedron, so a triangular based pyramid. So this is most useful when you're in 2 dimensions. And if you go above 4 outcomes, then you need lots of dimensions. You can't visualize it anymore. But for small numbers of outcomes, I find this useful. And we're going to come back to this idea in, I think, next week. Okay, so here's the kind of crux of the point, which is why we're talking about this. So there's a very old result called the von Neumann-Morgenstern expected utility theorem, which says exactly when preferences on distributions of outcomes can be represented by expected utility. So you can't always do this. So von Neumann and Morgenstern proved that you can do this. So you can represent preferences on probability distributions of outcomes exactly when two conditions hold. And I'm not going to say them exactly because they're kind of technical and mathematical. But the first condition is called continuity, and it roughly says that if you make very small changes of probability, then in the limit, your preferences can't change. And so the TLDR from kind of the psychological economics is that human decision-making usually satisfies this one. The second condition is called independence, which says roughly that if you take weighted mixtures of probability distributions, then preferences change in a kind of compatible way. And this one is very often violated by human decision-making. So this is kind of interesting because every time that this fails, you're not allowed to use numerical payoffs. It's not valid. But of course, everyone does it anyway. So the TLDR is we have to use numerical payoffs in order to do anything at all with game theory. The whole field is kind of mathematical. It's about real optimization. But these conditions are sort of implicitly in the background all the time. So we're never going to mention this again. But every time we write some real numbers that are outcomes of some decision making, implicitly there's another step, which is that there are some outcomes which are qualitative, and then we have an expected utility function, which is assigning an expected utility to probability distributions on those kind of qualitative outcomes that we never write down.